Everyone. Again, my name is Saud AlKhaled, and for the next 10 minutes or so, I'll be sharing a piece of our work titled Drivers of Intra-Urban Thermal Variability and Latent Magnitudes of Heat Mitigation Strategies in a Hot Urban Desert City, the case of Kuwait. So first, one might ask, why Kuwait, and maybe probably the relevance of hot urban desert cities, or HUDs as I call them. And here the climate attribution of hot is based on the Köppen-Geiger climate classification system, specifically urban areas falling within the BWH climatic subtype, within which intra-urban thermal variability is often attributed to differences in built environment features and surface characteristics, as with any urban environment. However, the dynamics of urban-induced heating in hot urban desert cities are in many ways different than their temperate counterparts, especially when they are compared to them in terms of structure and timing, as we know from the literature, many of which are here with us in this conference in terms of urban cool islands, oasis effects, or heat sinks as they have been observed in hot urban desert cities. In addition to being underrepresented in terms of research investigating urban heat mitigation strategies, desert cities of the Middle East, in particular within the Arabian Peninsula, despite the lack of available natural resources, are experiencing rapid growth of infrastructure and populations. In this study, we attempt to investigate the drivers of spatiotemporal thermal variability across the hot urban desert city of Kuwait, while utilizing the natural heterogeneity available in the built environment features and surface characteristics. And we ask, how do these relationships between built environment features and surface characteristics and urban-induced heating variability behave across the diurnal cycle? And we're not targeting urban heat islands here, we're targeting urban-induced heating or intra-urban thermal variability. We took a mobile surveying approach, where the criteria used to evaluate the efficiency of the traverse path included three parameters. The first, the impact of vehicle traffic on data collection, and here it's a left-hand dominated traffic, and you'll see that we took a clockwise approach to bypass any traffic lights within the traverse path. The second would be the coverage of built environment features and surface characteristics, and third is the duration of the campaign, to be less than 1 hour to ensure relative stable boundary conditions as found in the literature, as well as the time of day effects. Field measurements occurred on a clear summer day, namely June 15, 2022, with low wind speed and no cloud cover. We followed the protocol established by Hart and Saylor in 2009, as I drove along the selected loop-type traverse path in a vehicle equipped with both a GPS data logger and a Vaisala weather transmitter, which operates within considerable accuracy and time response for a mobile monitoring setup, recording at 10-second intervals and traveling at 18 meters per second or 65 kilometers per hour. This is a selfie of myself and the rigging of the car used just after I was stopped by a police officer, but this is something I can probably discuss later. We relied on several stationary or fixed weather stations to establish the background conditions, all of which were at a distance from 10 kilometers to 100 kilometers away from the center of the transect route, averaged those of the observations, and determined the background weather conditions. To capture the system dynamics, if I may, of summertime urban thermal stimuli, transects were conducted at 3 hours, namely midday at 10 a.m., mid-afternoon at 4 p.m., and evening at 8 p.m., as highlighted over the background weather conditions in this chart. And to control for the time-lapsed effect, as highlighted clearly, we used a simple linear detrending and applied it to the spatial temperature data. To investigate the relationships between physical factors and urban-induced heating variability, field observations were coupled with results of a high-resolution geographic object-based image classification, otherwise known as the GeoBia. And the aerial image was classified into 6 predictor variables, namely building, asphalt, pavement, sand, trees, and shade. And I trained that classifier to distinguish between trees with canopy versus low-lying vegetation. So not everything green is trees, or not everything green is vegetation. So there's a tree with canopy, or there's grass, shrubs, and hedges, etc. Each observation here was then coupled with results of 3 buffer sizes, starting at 2 kilometer radius by half-length intervals, so meaning 2 kilometers, 1 kilometer, and 500 meters along the transect. And then statistical analysis were further conducted using this composite data set to identify the urban effects on intra-urban thermal variability. As we started mapping the detrended thermal traverses, we started noticing how air temperature variability along the route wasn't consistent across the different times of interest. So we clearly see that they are not alike in midday, mid-afternoon, and evening, which is not surprising. However, it is surprising when we see that even during the day, there's some sort of variability. And what I'm trying to say is that, for instance, hot spots and cool spots were not the same. So it's not only a daytime, nighttime comparative, but even within the day, we can see some significant variability, and the magnitudes are also different. And this is clear when we look at the midday on the far left, comparing it to the mid-afternoon and in the evening. And to understand what could really motivate or influence such variability, we plotted the built environment features and surface characteristics against these observations and found significant primary relationships, as I will be discussing in a few slides. But we can clearly see the relative contribution of the surface fractions or the built environment features and surface characteristics as we look at these hotspots and cool spots. Which was obviously done across all observations along the transects, not only the cool spots and hot spots. And of course, across all buffer sizes as we travel on the slide vertically, the 500, the 1 kilometer, and the 2 kilometers. And what can be noticed, and this is why I have the slide here, is how the granularity of the built environment features and surface characteristics are rather smoothened, which is something that we expect as we increased the buffer size. Now, correlation associations as well as significance were found to be rather consistent along the three buffer sizes. And this is clear when we see these profiles, right? When we see the 500, the 1 kilometer, and the 2 kilometers, the profiles are rather the same. The only difference we found was the strength of these associations. Generally, as highlighted here, the significant relationships were found at 500 meters in midday and at 2 kilometers in the afternoon as well as the evening. During midday, moderate negative relationships were found for trees, asphalt, and pavement, which is something we expect and could be explained by shade from trees, as well as specific heat capacity of asphalt and pavement as they have been recharging during the night to accept solar radiation in the morning. However, the most significant relationship was a positive influence and found for shrubs at 500 meter buffer, which could potentially be explained by effects of irrigation-induced warming as found in the literature. However, this wasn't the focus of the study and should be evaluated later. During mid-afternoon, the most significant relationship was both positive and negative, found at 2 kilometers for building and sand. Other moderate positive relationship was also found for trees, and with that we start seeing here the inverse of the association between midday and mid-afternoon. So it's more than a nighttime, daytime comparative. Within daytime still, so we're still at 4 p.m. and we still see this flip of association between trees in midday and trees in the mid-afternoon. Finally, in the evening, the most significant relationship was negative for sand at 2 kilometer buffer, which also makes us question the issue of compact versus open and all in between morphology, specifically for hot urban deserts. And as expected, of course, a positive relationship was found, so a heating effect was found with buildings and trees in the evening. So these initial findings suggest the importance of identifying predictors of urban-induced heating with respect to subdiurnal phenomena. Quantifying these relative importance of these effects highlights the significance of considering temporal variability aspects within urban heat mitigation strategies, especially in hot urban deserts. So our key findings here can be summed into 6 points. Influences and associations vary hourly. Buffers did not show a significant effect, although I assume if we reduce the buffer size from the 500 meters, we might start seeing the different relationships. It's more than a day and night comparative, as I have been saying, as we've seen from the 4 p.m. and the 8 p.m. transect results. Also, the issue of potentially urban-induced or irrigation-induced heating during the day. Reconsider the literature with regards to sprawl versus compact in hot urban desert cities, as we've seen. And finally, heat mitigation should be considered in a site and time use basis. Who's there and at what time? There is no silver bullet here. Lastly, limitations and future work. We only have select hours. I'm hopeful that in the future I can continue working on this, both in terms of time of day as well as across the seasons. A limitation is these findings could be specific to Kuwait in terms of their physical and anthropogenic attributes to Kuwait. And lastly, the research design is a correlation design, I have to mention this, and not causality. I only indicate the likelihood impact of the built environment features and surface characteristics on air temperature variability. Thank you.
So